Okay, so let's just jump right in. Have you ever stopped to think about how your computer remembers things compared to how your brain does? I mean, they are fundamentally almost alien to each other. A computer, it's like this super meticulous librarian. It stores every single piece of data in a very precise location with a very specific address. Your brain? Whoa, that's a completely different universe. You know, a great way to picture this is to think of a file cabinet versus a spider web. Your computer is that file cabinet. To find something, you have to know its exact address, drawer C, folder 12, document 3. If that address gets even a little bit messed up, poof, the file's gone. It's incredibly brittle. But your brain is like a massive, shimmering spider web. You don't remember stuff by an address, you remember by association. The smell of cinnamon might make you think of your grandma's house, which connects to a memory of her dog, which then reminds you of a funny dog video you saw yesterday. It's this beautiful web of connections. It's robust, it's a little fuzzy, sure, but it's unbelievably powerful.
So that leaves us to the huge question at the heart of this research. What if we could actually build a computer that thinks less like a file cabinet and more like that spider web? I mean, what if we could build a machine that actually remembers like a brain?
Well, the answer, it turns out, might just be found in this really fascinating field called hyperdimensional computing. It's a totally new way of looking at computation, and it gets its inspiration directly from the sprawling, interconnected wiring of our own minds.
So, what is this stuff? At its core, hyperdimensional computing, or HD computing, represents information in a completely bizarre way. Instead of the usual ones and zeros stored at a specific address, every single piece of data, whether it's a letter, an image, or even an idea, gets transformed into a gigantic pattern called a hypervector. Think of it like a unique, incredibly complex fingerprint for everything. But this fingerprint doesn't exist in our world, it exists in a mathematical space with thousands of dimensions.
And to give you a sense of scale here, the researchers in this study were using hypervectors that have 10,000 dimensions. Yeah, you heard that right. 10,000. It's kind of hard to even wrap your head around, but it's that immense scale and complexity that gives these things their power. And these hypervectors, they have what you could honestly call superpowers. First off, they're holographic. This is cool. It means the entire piece of information is kind of smeared across all 10,000 dimensions. No single part of it is critical. This quality makes them incredibly robust. You can literally damage or lose a huge chunk of the hypervector, and you can still get the original information back. And finally, they're associative. You don't look for a perfect, exact match. You just look for what's close enough, what's similar. Just like how one memory in your brain can trigger a totally different one. Okay, I know, this all sounds pretty abstract, right? So let's bring it down to earth with a concrete example the researchers used. They put this brain-like memory to the test by teaching a computer to recognize different languages just from a little snippet of text. So here's how it works. First, the system takes letters and common letter combos and turns them into their own unique 10,000 dimension hypervectors. Then, it grabs a sample of text, say a paragraph from an article, and it bundles all those individual patterns together into one single query pattern that represents the whole paragraph. Step 3 is the search. The system then compares this new query pattern against a whole memory of patterns it's already learned for English, Spanish, German, you name it. And finally, it figures out the language just by finding the closest match. See? Not a perfect match, but the one that's the most similar. It's basically pattern recognition on a colossal scale.
And this right here, brings us to the absolute light bulb moment of this research. Because the whole system works by finding the closest match. It doesn't need to be perfect. The brain's tolerance for being a little fuzzy, for making errors, that's a feature, not a bug. And it's a feature you can actually hack to get incredible efficiency.
And this isn't just some small side benefit. It's the central property that the researchers realized they could totally exploit. They put it perfectly in the paper, saying, HD computing is amazingly tolerant to error. And just look at this graph from the paper. It shows you exactly how tolerant it is. It's tracking the accuracy of the language recognition as they deliberately introduce errors. Get this, you can flip 3,000 of the 10,000 bits. That's a 30% error rate. And the system's accuracy is still hanging out above 90%. A normal computer would have just completely fallen apart way before that. It's wild.
This incredible toughness sparked a truly brilliant idea. The researchers thought, hey, if this system can handle this much error without even breaking a sweat, what if we intentionally designed hardware that wasn't perfect? What if we could trade just a tiny sliver of that amazing accuracy for a massive win in energy efficiency?
And that is exactly what they did. They started exploring techniques like voltage overscaling. It's basically like running your computer chips on less power than they're supposed to get, kind of like putting them in a permanent low power mode. Now, this makes them more likely to make little mistakes, but as we just saw, the HD computing system just doesn't care about little mistakes. And the result, as this graph shows so clearly, is a direct trade-off. The more errors you're willing to accept, the more energy you save.
So let's break that down. One method they tried was just ignoring parts of the hypervector, just sampling it. That alone saved about 25% on energy while keeping the accuracy pretty high. But the real game changer was that voltage overscaling. By running the hardware on lower power and just letting the errors happen, they saved over 50% in energy. Think about that. They made the hardware worse to make the entire system drastically better.
So, okay, zooming out, what does all this mean for the future? Why does hacking the way the brain remembers matter so much for the next generation of AI?
Well, this research basically unlocks a whole new road forward. It points the way to building incredibly energy-efficient AI systems, which, let's be honest, is one of the biggest problems in the field today. It lets us bypass the old, brittle way of doing things and gives us better tools for all those fuzzy tasks that our brains are so good at, like recognizing images, making analogies, or pulling together data from a bunch of different sensors. The paper even suggests this approach could lead to a nearly 20-fold improvement in the energy delay product. That's a key metric for computer performance. That's not just a small step, it's a monumental leap. And this all leaves us with one last, really fascinating thought to chew on. For years now, the story of AI has been all about bigger models and more data. Just throw more data at it. But maybe that's about to change. Maybe the next great leap in AI won't come from the software at all, but from the hardware itself. Maybe it's not about feeding the beast more data, but about finally learning how to build a better, more efficient, and fundamentally different kind of brain.